Blockchain technology, the underlying software code that makes Bitcoin and many other cryptocurrencies function, is itself a valuable and powerful enabler of innovation. Beyond cryptocurrency, blockchain is redefining how we store and update transactions on a network. It's also enabling a completely novel way to write and deploy software applications that redefines our notion of how solutions are deployed, owned, and managed. It's demonstrating the power to improve online security and trust. Blockchain is even enabling the creation of a new type of organization that can function without centralized leadership and decision-making. And in the future, blockchain may even enable a new version of the internet where each of us can own a part of it. Hi, I'm Dr. Jonathan Reichenthal, founder, professor, and author. Welcome to this advanced course on blockchain technology. As a follow-up to my popular Blockchain Basics course on LinkedIn Learning, it's now time to go deeper into the technology and its applications. Specifically, we'll explore the details of how blockchain works and how you can unleash its remarkable power. We'll also look at unique implementations of blockchain technology in a variety of contexts. For example, we'll discover solutions such as decentralized finance, non-fungible tokens, and identity management. Get ready to explore blockchain in depth. I'm confident that you'll appreciate its enormous potential and recognize ways it can help you empower solutions, old and new alike. I'm delighted to share with you an expanded journey through the blockchain universe. It's time to begin. Let's go. Since this is an advanced course, I'll assume you already understand the basics of blockchain technology. If not, I encourage you to first watch my Blockchain Basics course. That course will provide the necessary foundation for much of what I discuss in this advanced course. In addition, this course assumes you have introductory knowledge of computing, databases, and networking concepts, and the associated terms. That said, this isn't a programming course. For example, we won't learn to code in Solidity, a blockchain coding language. If programming is where you want to go with cryptocurrencies, crypto tokens, and blockchain technology, and I hope many of you do, then this course will help to prepare you. Finally, it's not essential, but I'd recommend reading Satoshi Nakamoto's Bitcoin, a peer-to-peer electronic cash system. It's readily available for free on the internet. It can get a little technical, but there's some excellent insights that you'll find enlightening and informative on your blockchain learning journey. It's time for us to jump in and discover what's under the hood of this fascinating technology. In the 2008 Satoshi Nakamoto paper, Bitcoin, a peer-to-peer electronic cash system, the proposal that kicked off the cryptocurrency movement, its main thesis was a solution to the double spend problem. The author recognized that a solution was required to eliminate the possibility of duplicate digital transactions in order to enable a viable digital currency. The proposal was for a distributed ledger where new transactions could only be added via participant consensus, and where all data would be linked cryptographically. This distributed ledger later became known as a blockchain. In the process of solving the double spend problem and enabling cryptocurrency, blockchain introduced a new way to store and manage data across networks. By validating transactions with a consensus mechanism rather than centralized and permission control, blockchain opens itself up to a completely new set of use cases. Suddenly, blockchain was being considered for all manner of novel solutions. The central business case for blockchain has become its ability to confidently validate transactions over a network without the need for centralized management and oversight. Today, the application of blockchain and its potential far exceed its genesis in Bitcoin. It supports not just digital money and trusted data movement and storage, but the exchange of value. At a fundamental level, it's not complex technology, but it can enable complex solutions. It can help solve some difficult computing challenges around security, and it introduces capabilities that are disruptive to the status quo. For example, cryptocurrencies effectively eliminate the need for banks and a whole host of financial middlemen. Taken further, blockchain technology can be used as a foundation for a new generation of software that distributes code across a decentralized network and enables transactions between individuals and machines without the need for complex server infrastructure. Blockchain supports a flat, peer-to-peer network architecture without any hierarchy, the opposite of what is found, for example, in traditional client-server environments. Just as the internet enabled new services such as the World Wide Web, email, and FTP, and all the significant benefits these solutions created, blockchain is quickly becoming a platform for a wide range of new business applications. These include areas as diverse as cross-border payments, supply chain management, online identity management, support for digital assets, and much more. With unique capabilities, blockchain opens up new business possibilities and creates the conditions for a whole array of disruptive innovation. Today, the internet plays a significant role in how we communicate, learn, work, and play, and so much more. It has decimated industries like the newspaper business, while reinventing others like e-commerce and how we manage our money. It has created vast new industries such as cloud computing, everything as a service, and social media. But this vast network of networks has some stubborn problems. We face continuing questions such as, is the person you are doing business with online really who they say they are? Is this online service that you're attempting to use actually a real business? Or is it a scam that's ready to take your money and run? These are all questions of trust, and there are many more. Healthy ecosystems rely on trust. This applies both in the offline and online worlds. Innovators have worked hard to solve these challenges, and we've come a long way. Yet we still get hacked and scammed. Our systems are compromised, made unavailable, and our money and identities are stolen. If we want, for example, online voting to succeed, confidence in digital money, self-driving cars that securely navigate the world, and better ways to authenticate online identity, we're going to need greater guarantees of online transaction integrity and a more trustworthy internet. Online trust has roots in how we manage data and databases. A core characteristic of a traditional database is that it has a central authority that governs it. For instance, an organization that creates a database has full rights to control that database. They could decide who has access and what type of access they can have. They decide what is stored in it, what is deleted, and what is archived. For the most part, this kind of control is beneficial, but it means that power over the system is limited to a small set of decision makers. This can be a bottleneck and create inefficiencies. With people-driven central authority, this can create opportunities for issues such as human error and bias. It also means that security vulnerabilities may be concentrated within a core set of people and systems. When databases power important solutions in the private and public sectors, system rights become a complex topic. In many cases, people remain the final arbiter of the validity of a transaction. As an example, we see this clearly in contract work. A contract between two entities completed over the internet often requires one or more central authorities to validate interactions. Let's look at the mortgage process. A financial institute must validate savings and approve loans. Title companies must validate property, and legal professionals must oversee signatures and other contractual requirements. Each one of these central authorities has unique powers that levy considerable overhead in a mortgage transaction. The mortgage transactions moving through a variety of systems all take time to process, cost money, are vulnerable to hacking, provide limited participation from those involved, require special skills, and can be error-prone. We've generally accepted these overheads as the price of all the advantages of doing work over the internet. Blockchain technology's unique design and function has demonstrated the capability to address many of these issues. At its core, its decentralized network design, coupled with cryptographically linked blocks of data and a form of network participant consensus, eliminates central authority and increases process and system integrity and security. Fundamentally, blockchain introduces the idea of trust through software code. These are the basic advantages of blockchain technology. Soon we'll go a lot deeper to explain how it all works. If the only success of blockchain was to enable cryptocurrencies, that technological achievement alone would be worth celebrating. By solving the double spend problem outlined in Satoshi Nakamoto's Bitcoin paper, an entire new category of digital money has been created, whose full story has yet to be told. What has surprised and delighted so many of us is that blockchain continues to mature into an ecosystem of technologies and solutions that are demonstrating novel value across industries. It turns out that a distributed system that adds new cryptographically linked transactions by consensus has many applications. Observing the unique capabilities of Bitcoin and blockchain, in 2013, Russian-born Canadian Vitalik Buterin, at the age of 19, led the founding of Ethereum. Ethereum supports an alternative cryptocurrency, or altcoin, called Ether, based on the same blockchain principles as Bitcoin. But it's much more than that. Ethereum turns the network of participants into a virtual computer called the Ethereum Virtual Machine, or EVM. It enables a low-cost, massively scaled computing platform. Applications called smart contracts, executable rules that run on blockchains, can be run on the EVM. All types of solutions are being built that include those for banking, managing digital assets, and gaming. Solutions take advantage of blockchain's distributed design to include flat hierarchies, eliminated middlemen, and immutable transactions. Altcoins in general are rapidly growing, both in number and often in value. Today, thousands exist, many offering specific capabilities. For example, Stellar is a blockchain network developed for the purpose of connecting banks and facilitating large transactions instantly and at low cost. Monero is an altcoin that operates like Bitcoin, but where transactions are private. Finally, Litecoin is a crypto that processes transactions faster than Bitcoin. Beyond cryptocurrencies, blockchain's growth continues. While natively a public-based permissionless ecosystem, blockchain offers advantages to private companies that are too compelling to ignore. Despite the inherent contradiction, private, managed, and permissioned blockchains have found a home within enterprises. The Linux Foundation, for example, offers Hyperledger, an open-source enterprise blockchain that features many of the qualities of a public blockchain, such as immutability and traceability, that is, being able to analyze the entire history of a stored record, but also with the privacy and control sought by a private organization. With its genesis in cryptocurrency, it's no surprise that the financial sector has been an early adopter of blockchain technology. Crypto proved that transactions could be safely and securely recorded on a distributed ledger, and this has provided the basis for expanded use in banks and other financial institutions. Primary among the uses are payment systems. In particular, cross-border settlements have been most widely adopted. Many banks now handle crypto too, while others are taking a more cautious approach. Analysts have projected that many blockchain experiments in the financial sector will begin to move into production systems over the next 5 years. In the rapidly emerging fintech or financial technology arena, an industry dominated by startups that are prioritizing the use of technology to improve finance activities, blockchain is gaining momentum. In particular, decentralized finance, or DeFi, What's surprising about the Satoshi Nakamoto paper I discussed earlier is that it does not mention the word blockchain. How could this be if blockchain is the enabling technology for Bitcoin? Turns out the paper uses a different term that predates Bitcoin and blockchain. Instead, Satoshi refers to distributed ledger technology, or DLT. Many technologists are inclined to use the term blockchain and distributed ledger interchangeably. It's not such a big deal that anyone should get their hands slapped, but they are different. We can think of DLT as an umbrella term for organizing transactions in a shared distributed system. Blockchain is just one type of DLT. Mentions of distributed ledgers go back as far as the Roman Empire as a way to record transactions across the far reaches of Roman rule. Indeed, ledgers themselves are thousands of years old. We've needed to be record keepers for a wide variety of purposes for a long time. Banks today, for example, use ledgers so that they can keep track of deposits and withdrawals. In this way, ledgers require an authority to ensure that they are kept current. But what happens when we remove the middleman, the central authority, as we do with cryptocurrency? It means the distributed ledger needs a mechanism for maintaining the integrity of transactions and ensuring that all entries are synchronized. We can't have double spending all over the place. Crypto would simply not be viable. This is what blockchain solves. In fact, blockchain simultaneously solves the double spend problem and the lesser known metaphor of the Byzantine generals problem. Okay, what exactly is that? Imagine multiple Byzantine army generals who split up in order to attack an enemy from a variety of locations. The generals must communicate over distance in order to coordinate. However, how can all the generals be sure that none of the generals are traitors and will send conflicting messages? This problem is analogous with a distributed ledger in that there needs to be a way that independent participants in the network will ensure that no participant will attempt to enter fraudulent transactions in the ledger, specifically the blockchain database. The problem is solved through a mix of mathematics, cryptography, and consensus. While I'll describe all of these in more detail in later videos, the process can be summarized like this. A transaction can only be considered a candidate to add to the distributed ledger if one participant has expended effort to solve a mathematical problem. The problem involves finding a predetermined, cryptographically derived hash value from an input. That input happens to be the contents of the transaction. The correct answer is broadcast to all the network participants, or nodes. Each of them has a copy or access to a copy of the blockchain database. Nodes validate the broadcast solution, and if they agree by consensus, then the transaction is approved to join the blockchain database. If an invalid transaction is broadcast, it will be rejected. The overall process is known as proof of work, and the participants that try to solve the mathematical problem are called miners. We can see how this particular type of distributed ledger, the consensus-based blockchain, has some really unique and powerful capabilities. Not all distributed ledgers are blockchains, but Bitcoin's ledger is the fundamental architecture for most cryptos today, and many of the unique solutions I discuss in this course. In my view, the best way to understand the details of how a blockchain works is to break it down into its component parts. In this video, I'm going to explain cryptography and the role of keys in blockchain. The term cryptography is a Greek word which means secret or hidden writing. At a basic level, it's a way to create a message so that only authorized individuals are able to access and read it. For everyone else, it'll be gibberish. Using cryptography, a plain text message, one that can be read, is converted to ciphertext. One that can't, it is said to be encrypted. When the message arrives at its destination, it must be decrypted so that it can be read again. Cryptography predates computing, and over centuries, many cryptographic tools have been used to encrypt and decrypt. Today, cryptography within computing is essential for data privacy and security. One of the most popular forms of computing-based cryptography is called public key cryptography, or PKC. It involves two keys, a public key and a private key. Everyone can see the public key, but only you have the private key, and it must be kept secret. PKC was invented in the late 1960s and provides a simple and powerful solution to cryptography. The first step is to have a private key generated. There's a lot of software to do this, as a private key is basically a random mix of letters and numbers. You can try it yourself at bitaddress.org. Here's an example of a private key. When a private key is generated, its pair is also created. That's the public key, and it's created using a complex algorithmic process. The process makes it possible to generate the public key from the private key, but makes it exceptionally difficult to figure out the private key from the public key. So how's it used? Whenever you want someone to send you something secret, you first send them your public key. The other person encrypts the message with your public key and then sends the message to you. You then open the message with your private key. Someone who tries to intercept the message will be unable to unlock that message. Only you can, because you keep your private key and you never share it with anyone. We can also use PKC for authentication. For example, if you send a message, how can the recipient know that it was sent by you for sure? Or if you claim that a digital item belongs to you, how can you prove it? For this, we use a digital signature. A long time ago, documents were sent in envelopes that were often sealed with wax, with a unique stamp in the wax. This way, the receiver knew that the envelope came from a trusted source and that it had not been tampered with on its journey. A digital signature is the digital equivalent of the wax seal. Digital signatures use public-private key pairs to function. When sending an electronic message, the message is signed with a private key. When the message is received, and assuming the recipient or system has access to the associated public key, it is used to verify that the signature was created with the private key of the sender. If someone attempted to bluff by using another private key to prove ownership of the digital item, the recipient would immediately be aware of the bluff because the public key would not authenticate with the false private key signature. When transactions are written to a blockchain, they are signed with a participant's private key. Later, they can access their transactions and prove ownership because only they have possession of the private key. With this insight, it should now make sense that it's the important role of cryptography in blockchain where we get the word crypto in the term cryptocurrency. Finally, we're not done yet with the role of cryptography. It plays another vital role in binding transactions together on a blockchain that ultimately provides another level of robust security. We'll explore that next. I'm going to cover a series of terms and concepts that, on the face of it, don't seem connected. However, before too long, I think you'll find that all the pieces will fall into line. Let's start with a nonce. Until blockchain, I'd never heard the word. A nonce is a number that is used once for a specific purpose and never used again. As an example, in an era of big data, there's always a possibility that data entered into a database may have the same identifier. Adding a nonce to some identifier makes it additionally unique, thus making it harder for accidental duplication. I'll return to the role of a nonce in blockchain in just a moment. Next, let's take a look at what a hash function is. A hash function is a mathematical process that takes data of any size, performs an operation on it, and returns a unique hash, data of a fixed size. Whether the input text is a single letter or a Shakespearean soliloquy, the resulting output hash is the same size. Any modification to the input changes the hash output. That said, for a specific hash generator, the same output will be generated for a unique input each time. For example, in the sentence called a string in computing, the man in the hat might provide a hash of this. And similarly, the word dog, also a string, may result in this. You can see that both strings resulted in the same size hash output, or signature. Converting a string to a signature is called hashing. Hashing only goes in one direction, something called a one-way function, and is a form of cryptographic encryption. Hashing has a wide variety of uses within computer science. The hashing process used in a Bitcoin blockchain is the Secure Hash Algorithm, or SHA-256, often pronounced SHA-256. I'll return to this shortly. The essential and core process of mining, another new term, is going to help us integrate the purpose of the nonce and hashing. In a blockchain network, a participant can choose to have the role of a miner. A miner, through their efforts, is incentivized to perform an important function because they have the chance to earn cryptocurrency. This critical function, called proof of work, is the consensus mechanism used to verify transactions, get them added to the blockchain, and create new crypto. It's miners conducting proof of work that makes the blockchain work. Let's explore this. When transactions are broadcast to the blockchain network, these could be crypto payments between individuals, then transactions are not automatically processed. To add new transactions to a blockchain requires that a specific hash output be determined from hashing the In my opinion, no study of blockchain is complete without a basic understanding of the birth of Bitcoin. Surprisingly, even today, we still don't know for certain who authored the Nakamoto paper in 2008. Who is Satoshi Nakamoto? He or she may even be a pseudonym for a group of people. This mystery adds to crypto folklore. It is believed by some that the paper and its proposal was a response to the financial crisis of the late 2000s. A notable global economic downturn was a result of bad loan practices, dubious financial schemes, and a brittle banking system. Confidence in the global financial sector was shattered. The Bitcoin proposal offered the opportunity to build a trustless monetary system in which banks and other financial intermediaries became unnecessary. People would be able to send money directly to each other, peer-to-peer, so to speak. Wait, but trustless? That seems unusual, right? I'll explain. The existing financial markets rely heavily on a system of trust. For example, you deposit money in a bank, and you expect and trust the bank to manage it for you. That reliance and trust has inherent risks. For example, many of us experienced the results of those risks loud and clear in the late 2000s during the Great Recession. People's homes were foreclosed, banks closed, jobs were lost, and the economy tanked. Satoshi's Bitcoin paper offered the prospect of a monetary system that did not rely on the trust of others, a trustless system. Risk would be reduced and the reliance on others would be eliminated. In early 2009, barely months after the paper was published, a first release of the proposed open source Bitcoin software appeared. Open source meant the code could be inspected, modified, and distributed by anyone. Satoshi's idea had become real, and it was ready to be used. The first Bitcoin to be generated and sent to a recipient was called the Genesis block. Blockchain-based cryptocurrency had arrived. From day one, Bitcoin introduced the novelty of a practical digital currency absent of any intermediaries or central governing authority. Money could be sent directly from a person to a person. Everything about Bitcoin challenged the contemporary understanding of money. For one thing, and perhaps most importantly, how could it have value? Briefly, for money to have value, it must meet at least 4 criteria. There must be a supply, a demand, a utility, and trust. Built into Bitcoin is a scarcity component. There would only ever be 21 million Bitcoins available. Why this number was decided is unknown. In addition, it's possible that a future version of Bitcoin may be modified to produce more. That said, this meets the supply dimension. Next is demand. For over a decade, there has been a steadily growing demand for Bitcoin. This interest and demand have many factors, including the possibility of making money off its growing value. a behavior that itself can drive the cost up, completing a virtuous cycle. There's also the incentive for miners to compete to win free Bitcoins, which is a form of competitive demand. Next is utility. In this case, it's simple. You can buy things with Bitcoin. From pizza to art, from technology products to entertainment, Bitcoin is accepted by a high number and a wide range of retailers and providers. Finally, trust. It seems unintuitive to discuss trust with a trustless system. What we mean here is that the marketplace has confidence that the ecosystem will operate in a somewhat predictable manner from day to day. For example, if I buy Bitcoin today, I should be able to sell it tomorrow. Users need to have a sense of confidence in the system. With over a decade of success, despite an ever-present risk of volatility, Bitcoin has performed well. More confidence also means more people are inclined to buy into its proposition. While considering these four dimensions, on some level, however, the value of Bitcoin at any point in time comes down to what the community of users believe to be its value. If enough people think it should have value, then it will. Taking a separate course in economics would be necessary to get to the heart of this. I hope after watching this video, you'll agree with me that Bitcoin is already the definition of successful disruption, regardless of what happens in the future. In the next video, I'll discuss in detail how Bitcoin is acquired and managed. The motivation for people to engage with Bitcoin and other cryptocurrencies are varied. In addition, we have to recognize that as the uses of cryptocurrencies rapidly evolve, the functions people perform with them also change. One rudimentary activity is to acquire crypto and then either keep it, called hodling, a play on the word holding that the crypto community has adopted based on a typo, or use it to buy something. Hodling is popular because over the past few years, with the rapid value appreciation of some cryptos, many who bought low are seeing massive gains. And just like gambling in a casino, timing a cash out from crypto can mean walking away with a healthy profit or losing a lot. So how does a user go about buying and using crypto? In the early days of Bitcoin, it was relatively difficult to acquire. Fortunately today, buying Bitcoin and other cryptocurrencies is much easier. A number of online exchanges have emerged that provide crypto management services. Coinbase, Binance, and Bitstamp are among the more credible exchanges, and many more exist to explore. Plus, traditional banks are getting in on the action too. Much like setting up a bank account, a user must typically first create an account on the service. Then they move fiat money, that is, government-issued money such as dollars, into the account. This can be done, for example, with either a bank transfer or with a credit card. From that point on, a user exchanges their fiat money for the crypto of their choice. There will also likely be an exchange fee. Exchanging fiat currency for crypto and back again follows the same principles as buying and selling any type of currency. The price you'll receive or pay is determined by the state of the market for that currency at any point in time. Since cryptocurrencies remain volatile and can fluctuate quite rapidly, there's an opportunity to realize significant gains and suffer sudden losses. Once you acquire crypto, you now have both a public and private key. Many people will just let their exchange manage their keys. For sure, it's simpler that way. However, the risk is that a user's private key could be compromised by a hacking of the exchange, and then it's game over. A private key is a single device for proving ownership of crypto. If anyone gets access to it, they have full control of your crypto and can move it quickly, such that there's no recourse. As a consequence, some users will opt to move their keys into their own wallets, hardware or software that stores keys. The public key that is assigned to the user becomes their receiving address. Specifically, if the user wants to receive crypto, say from a buyer of a product or service, they simply provide their public key, and the buyer sends crypto to that key. Similarly, if the user wants to buy something with crypto, the seller will provide their public key. There are a lot of great apps to facilitate this that are easy to use, such as MetaMask and Exodus. As crypto and blockchain technology by extension has matured and been more broadly adopted, the supporting tools such as exchanges and apps have been improving. This is helping a greater number of people to participate. It's still not super simple and intuitive, but we're getting there. For many, Bitcoin is considered synonymous with cryptocurrency. Today, it is still the biggest and most successful, but the cryptocurrency ecosystem is much larger than a handful of dominant cryptos. Some estimations put the figure at over 10,000 independent circulating cryptocurrencies. We call these alternative coins, or altcoins, and they include names such as Ethereum, Litecoin, Cardano, Polkadot, and Stellar. Whether such a high number of altcoins can continue to succeed in the long term has yet to be seen. Incidentally, we call alternative blockchains altchains, those that are distinct from the Bitcoin blockchain. What is driving so many cryptos? Well, one answer is that they're a business and there's money to be made. For example, since just about anyone can create a crypto, the founders can keep a percentage for themselves and then just wait to see if the value increases. However, another way to look at the diversity of cryptos is through their utility. Each cryptocurrency can have its own monetary policy. It can use a different consensus mechanism, and it can have a specific function. Ripple, for example, is a utility that supports rapid cross-border payments, and it is supported in its function via its own crypto called XRP. Ethereum is an application development platform with a crypto called Ether that is used as a payment system for the applications built on the system. Polkadot is a crypto and a platform that facilitates interoperability among different permissionless and permissioned blockchains. What I've been describing so far are cryptocurrencies, sometimes referred to as crypto coins, digital money that runs on their own blockchains. But blockchain is at its heart a bookkeeping system. It can store and manage all manner of transactions. Let's look at this. While altcoins are also synonymous with crypto tokens, or simply tokens, there's another characterization of tokens in a blockchain space. While crypto coins have their own dedicated blockchains, such as Bitcoin and Ethereum, tokens are a type of cryptocurrency that use existing smart contract-powered blockchains. For example, the applications that run on top of Ethereum, a smart contract platform, use tokens for a wide variety of functions. Like crypto, tokens can hold value and be exchanged, but they also can be used to represent physical and digital assets and deliver specific services. Two major types of crypto tokens include security tokens and utility tokens. Security tokens represent whole or fractional ownership of any asset that already has value, such as real estate, a car, or corporate stock. For example, a person could own a token that represents a 5% share of a boat. Utility tokens give users access to a future product or service. For example, a startup could issue utility tokens to users to raise money, and later users could utilize the tokens to use the startup service. A third type of token, a non-fungible token, or NFT, is discussed in a later video. By understanding the crypto coin and crypto token space, it becomes evident that the blockchain ecosystem is becoming a vast catalog of cryptos and capabilities. When we discuss blockchain technology that supports capabilities such as cryptocurrencies and tokens, we're typically referring to public, permissionless systems. For example, with Bitcoin and Ethereum, everyone can participate in these networks. Permission is not required. In addition, much of the content on these and other public blockchains is transparent. There is an unexpected amount of data that can be easily observed. The data is immutable, permanent, and auditable to the very first issued block. These qualities are some of the advantages that blockchains have over other technologies and are directly supportive of their unique value proposition. However, what happens though if we want all the advantages of blockchain technology but need to have a system that can keep data private, that only permits access by certain people and doesn't require its own cryptocurrency? This is where a permissioned private blockchain becomes necessary. In response to this variation on the blockchain theme, in 2015, Hyperledger was created. This open source project was coordinated by the San Francisco-based Linux Foundation as a cross-industry collaboration involving technology companies such as Cisco, VMware, IBM, Intel, JP Morgan, and Wells Fargo. The objective was to create blockchain distributed ledgers capable of supporting global business transactions by major technology, financial, and supply chain companies, where all the participants are known as opposed to anonymous. One of the first releases of the software was called Hyperledger Fabric. Unlike public blockchains, it was designed to support private transactions, scalability, and a modular design. It supported the integration of existing software solutions such as IBM's Bluemix, a cloud-based architecture for creating, deploying, and managing cloud applications. It even had a smart contract type solution they called chain code, a way to build applications on a blockchain. I describe smart contracts in detail in a later video. Today, Hyperledger has become a hub that provides the design, philosophy, infrastructure, and standards for a wide range of blockchain-based projects. Organizations can adopt modular blockchain solutions and services and apply them to relevant operations within their enterprises. Private blockchains appear to have a role in the broader blockchain ecosystem. Organizations want the benefits of qualities such as immutability, transaction traceability, and decentralization. But they want more central control and authority over who has access. Sure, it's somewhat against the spirit of distributed ledger technology, but nevertheless, there is a market need. This leaves us with little doubt that blockchain will have value as a public and as a private network. While the Bitcoin blockchain continues to dominate the cryptocurrency space today, the second crypto-powered blockchain leader in terms of both market capitalization and uses is Ethereum. Ethereum's peer-to-peer network is made up of participant computers collectively called the Ethereum Virtual Machine, or EVM. It's decentralized and trustless and uses the proof-of-work consensus to add blocks. While currently stalled, Ethereum is preparing to move its consensus mechanism to proof-of-stake sometime in the near future. Instead of cryptocurrency as the end goal, Ethereum enables programmers to use a proprietary language called Solidity to write code that is distributed across the EVM. In blockchain parlance, we call this code a smart contract. Stated simply, a smart contract is software code that executes based on meeting predetermined rules. Smart contracts enable distributed applications, also known as dApps. But why code on a blockchain? Historically, most enterprise-class applications have relied on expensive and redundant architecture. Everything from identity management to storage must be provided and supported. In addition, several layers of code to enable security, scalability, and logic create costs and performance burdens. For a developer, Ethereum provides the possibilities of a low-cost, massively scaled, and secure application platform right out of the virtual box. The EVM avoids censorship, downtime, since there's no single point of failure, fraud, and third-party interference. In particular, dApps can be trustless, not relying on the attendant challenges of governing authorities. The magic with Ethereum is that when smart contracts are executed, its crypto ether acts as a method of payment and authentication. Imagine writing an Ethereum application that enables a person to play a premium-based LinkedIn Learning training video. The code will be executed upon confirmation of ether payment. There are no additional requirements for additional authentication methods, payment gateways, account management, credit cards, or complex forms. In this example, when the smart contract conditions are met, LinkedIn gets paid and the buyer gets access to the video. Compute time on the EVM requires units called gas. Gas is a measure of the computational effort required to run some specific code. So when a user runs the code within a smart contract, they must make sure it has enough gas, which is paid for with Ether. The number of dApps is growing rapidly. Solutions exist in areas such as finance, art, technology, and gaming. You can take a look at many by visiting this website. If you're interested in programming smart contracts, you'll need to use a JavaScript-like language called Solidity. You can develop Solidity code on a variety of available integrated development environments, or IDEs, such as Remix and Truffle. When ready, you'll want to test your smart contract in a simulated Ethereum environment called a testnet. Solutions include Ganache and Ropsten. Since programming is outside the scope of this course, I suggest checking out the Building Ethereum Apps courses on LinkedIn Learning from Michael Solomon. Of course, you'll find a lot of other great learning options online and in a growing catalog of books. Ethereum illustrates the enormous potential of blockchain technology. Rather than a technology limited to decentralized digital money, blockchain opens up a completely new way of thinking about developing, deploying, and executing software. While the future for Ethereum and other similar solutions is still unpredictable, the winners that do emerge will help to create the next generation of capabilities on the internet. Blockchains support crypto tokens, also referred to as simply tokens, a type of cryptocurrency that can represent an asset or have a specific function. A type of token that has exploded in popularity is a non-fungible token, or NFT. So what exactly is an NFT? When something is said to be fungible, it is the quality of an asset, an item of value, to be exchanged equally with another asset of the same type. For example, the notes and coins of currency are fungible assets. If I have two $5 notes, I can exchange them with another person who provides me with a single $10 note. Or I can swap my two $5 notes for another set of $5 notes. Although the notes are different in both examples, they have identical value and can be substituted for each other. On the other hand, non-fungible assets may be similar items but hold different values. They can't be substituted. For example, if I lend a friend my car, and when he returns it to me, he suggests giving me another car that is the same color, it's not a fungible exchange. Even though the car is the same color, make, and model, it may be a different year. It may have more mileage. It may have more wear and tear. Any differences like these changes the value of the asset and thus eliminates its fungibility. Enabling digital assets such as images to be certified as unique has been a remarkably tough problem to solve. Fortunately today, blockchain with the support of smart contracts have built the conditions for an emerging and thriving marketplace for digital assets. This has been achieved by creating a certificate in the form of a non-fungible token, or NFT, that lives on a blockchain and can certify that a digital asset is unique. NFTs are providing an efficient and verifiable way to buy, sell, and prove ownership over digital items. It's a breakthrough for creators, traders, collectors, and others of digital content. When selling digital items, a creator now has the option to assign one or more as unique versions of the digital asset. Each asset is issued a unique NFT that contains authenticity data. That NFT is then stored on a blockchain as a tamper-proof, immutable transaction. Note, however, that with many NFTs, a buyer may not be getting ownership of an item. They are simply getting a version that is digitally signed by the creator. Today, the most popular blockchain to store and trade NFTs is Ethereum. Other blockchains are emerging for NFTs, but the relative maturity and support in Ethereum and its smart contract capability has established it as the main platform. In 2018, Ethereum implemented an NFT standard called ERC 721. ERC stands for Ethereum Request for Comments, and this was the 721st. What ERC 721 does is implement an application programming interface, or API, between other applications and the smart contract-driven tokens on Ethereum. This is required because NFTs are typically managed on a growing ecosystem of third-party solutions. ERC 721 connects those applications to the token store on the Ethereum blockchain. You can learn more about ERC 721 by going to this website here. It's worth noting that ERC 1155, a more sophisticated standard, is becoming popular and may overtake ERC 721 in the future. It may also be of interest that the Ethereum standard for supporting fungible tokens is ERC 20. Whether NFTs succeed in the long term has yet to be determined. although the evidence is building. Regardless, for now, once again, we see that blockchain delivers a unique solution in an efficient and elegant manner. I think we're still only teased by the future potential of blockchain. Although blockchain has made significant inroads into the financial sector through support for cryptocurrency services and capabilities such as quicker cross-border payments, now blockchain technology is beginning to support an entirely new emerging ecosystem of finance solutions. Decentralized finance, or DeFi, is the term being used to describe blockchain-based applications that are disrupting financial services. Promised as far back as 2013, DeFi is now finally being realized as a serious contender within the fintech industry, which is technology and innovation that is competing with traditional financial services. DeFi applications are currently primarily built on the top of Ethereum, today, when a person or organization uses a financial institution to send a cross-border payment to another entity, say from Rotterdam to Hanoi, this transaction can take many days and incur significant fees. The global financial system is complex, bureaucratic, and has many intermediaries. I've personally sent money via my bank to other countries many times, and without paying an additional expediting fee, it's often taken several days. Additionally, because of the often sizable fees, sending small payments cross-border becomes restrictive. That's not great for the sender or the receiver, but that's the way it is generally today. How might this be solved? Let's look at a popular blockchain-based solution called Ripple. Ripple has developed a decentralized network of payment providers, such as banks, called RippleNet, to provide reliable messaging and real-time clearing and settlement of financial transactions. The network includes over 300 institutions across 40 countries. Its secret sauce lies in using both blockchain and its own crypto, XRP, to power the network and enable fast cross-border payments. RippleNet supports what is being termed the Internet of Value, which is about sending information over blockchain as easily and reliably as cryptocurrency. Let's use an example to describe how this works. Sakir in San Francisco wants to send $1,000 immediately to Asma in London. He also wants to avoid the high costs associated with fast payments on the more traditional cross-border payment systems. Fortunately, both Sakir and Asma's bank belong to the RippleNet network. In traditional payment systems, the sender must own the recipient's currency, or both participants must agree to convert to and from US dollars, a popular global currency. This conversion process provides some of the rationale for why traditional systems incur delays and fees. With RippleNet, a native cryptocurrency called XRP provides the vehicle for sending and receiving payments. Sakir's transaction is processed by the San Francisco bank by sending the equivalent amount in XRP to the London bank. The San Francisco bank may already hold XRP, can buy it from an exchange, or access it from a liquidity pool. At the London bank, the XRP is accepted and then can be converted later to British sterling. XRP acted as a 100% reliable bridge currency. In this way, it acted similarly to the role of the US dollar in global currency exchanges. However, XRP provided transparency and status at all times. It also eliminated the possibility of errors. Finally, what would have typically taken days is now achieved reliably in seconds. Both Sakir and Asma are happy customers. You know who you are, but how do others know? In the offline world, we use a variety of methods to prove our identity, such as a driver's license, a passport, or a birth certificate. These methods, issued and managed by central authorities, are effective, but they carry enormous risks, such as theft, fraud, and loss. They're also not sufficient for the enormous needs of identity management in the online world, a place where, for most of us, proof of one's identity is required often. In computing and online, authenticating yourself is called Identity and Access Management, or IAM. This consists of the technologies and processes to digitally identify and authorize access to systems and services. Like offline, online identity management has vulnerabilities such as hacking. Hundreds of millions of online identities, including credit card info and passwords, are compromised each year. Current IAM relies heavily on centralized authentication systems, which concentrate risks. They also don't often provide portability, the ability to use a common login name and password on disparate systems. Rather, most of the time, particularly outside an enterprise, we're entering unique credentials for each system we need access to. Single sign-on within organizations, the ability to use one set of credentials for different business systems, has helped, as has federated identity management. Examples of these include services such as logging into a service with your Facebook or Google credentials. In these solutions, you're giving away some personal information and you're relying on a great deal of trust. Fortunately, with the advent of blockchain technology, another solution has emerged that appears to address the weaknesses of current IAM. Called self-sovereign identity, or SSI, this approach to identity gives the user control over their personal data and what data will be shared. SSI is an identity you own without the need for a third-party provider to store and centrally manage anything. With SSI, digital identity is managed in a decentralized manner. The basic structure involves three parties, referred to as the trust triangle. There is the issuer, the holder, and the verifier. The issuer is the body that has granted the credential. For example, the driver's license authority would be an issuer of a driver's license. The holder is you, and the verifier is the party needing to attain proof of the credential. Ideally, the verifier does not need to actually see the data within the credential, just confidence that it is accurate. This is called zero-knowledge proof, and it's a quality of SSI. Let's explore the driver's license example further. In an SSI environment, upon qualifying for a driver's license, the driver's license agency would publish a transaction on a decentralized blockchain that confirms your license details. The agency would also send a signed certificate that contains all your information, including the transaction ID, on the blockchain to you, that you would store in your digital wallet. When proof is required by a verifier, You then present some or all of the details from the agency certificate. This is where you get to decide how much to share. The verifier then uses the agency certificate information to check against the blockchain transaction and validate that all is in order. At no time does the verifier need to check with the issuer. This is because they have a certificate from the holder that proves it came from the issuer, and the details are validated on the same decentralized blockchain it was originally published to. While it's relatively early, adoption of SSI is growing rapidly. This elegant architecture may hold the promise of portable digital identity and a more secure future. In many places in the world today, difficulty accessing quality, trustworthy information on land assets such as properties and who owns them is a serious impediment to rights and economic development. It's estimated that around $9.3 trillion in global land assets are undetermined because of inadequate processes to prove ownership. Unfortunately, land registries are often subject to corruption, and many properties have conflicting claims. In some communities, property information captured and stored on paper has not been converted to digital. This creates enormous risk. For example, in 2010, the devastating earthquake in Haiti that left 1.5 million people homeless also destroyed 60 years of paper-based land registry information. After the collapse of the Soviet Union in 1991, the newly independent Republic of Georgia, a country at the intersection of Eastern Europe and Asia, had to embark on rapid improvements in their civic enterprises. Property records, for example, were in bad shape, and in the turmoil of the post-Soviet collapse, they were plagued with high levels of fraud. For example, in popular tourist destinations along the Black Sea coast, many properties had multiple claims of ownership. In recent years, reforms in the Republic of Georgia have increased transparency in their land registry system. Despite these efforts, Georgia's National Agency of the Public Registry, or NAPR, was still subject to data integrity issues, resulting in a skeptical public. Subsequently, the NAPR embarked on a process to identify a solution that could protect the registry from manipulation and external cyber attacks. In 2016, the NAPR started to deploy the first phase of an updated land registry system based on blockchain technology, a first for both the underlying technology of blockchain and its applications such as cryptocurrency, NFTs, and DeFi can be viewed as a form of works in progress. Remember, many of the remarkable capabilities that are being demonstrated today are barely more than 10 years old, and some are much more recent. There's no doubt that we're seeing stunning benefits, but these should be viewed through the lens of elevated risk. Cryptocurrencies like Bitcoin and Ethereum, while continue to produce increasing value, could at a moment's notice collapse. Less known and mature cryptos, for example, have already shown extreme volatility, including some that have lost most value or have proven to be fraudulent schemes. It's common to hear the adage, only invest in crypto what you don't mind losing. However, with blockchain advancing steadily into the enterprise and consumer spaces, and real solutions emerging, there's reason for optimism that the opportunities are outweighing the challenges. Increasing numbers of organizations are showing interest and getting engaged in blockchain development. In one recent PwC survey of 600 executives, the number was as high as 84%. That percentage includes a range of efforts from simply learning and researching the tech to those experimenting with it. It is notable, however, that the actual number of organizations with an in-production blockchain system was only around 15%. So while promising in terms of overall engagement, there is clearly some hesitancy. In the PwC survey and others, some themes have emerged in support of why adoption and in-production use are not yet higher. Barriers cited include regulatory uncertainty, lack of trust among users, interoperability and integration limitations, scalability issues, and security risks. Clearly, these are not trivial concerns. With maturing technologies and improving results and case studies, it's only a matter of time before many of these concerns diminish. Significant work is still required to improve the overall security of the technology. This always feels unintuitive, given that blockchain by default makes claims of being more secure. But too many continued news stories of breaches, scams, and stability issues suggest a lot more security advances are required. For increasing the maturity of the technology, the blockchain community will need to work on advancing standards and interoperabilities. These areas are moving quickly, and there's a reason to be optimistic. One glaring area of concern, and perhaps a reason why trust in the technology remains low, is the lack of understanding of blockchain by senior decision makers. For too many, it remains synonymous with cryptocurrency, often Bitcoin specifically, a topic that is still viewed with much skepticism from those unfamiliar with how it works. Many more leaders need the opportunity to learn about the technology. Video courses like this one and others, and a wide variety of educational modalities must continue to propagate in order to reach a wider audience. Finally, the power-intensive requirements of the popular blockchain consensus mechanism proof of work is an unsustainable proposition. Blockchain has a community of supporters that see the technology as a passport to a better way of doing things. They are from communities often driven by social progress and better environmentalism. For example, many see blockchain as a way to create a more level playing field in the financial world. So it's with much concern that the technology is gaining a reputation as a contributor towards carbon emissions. Efforts are underway to move some popular blockchains to alternative consensus mechanisms, such as proof of stake. But for many, it can't come soon enough. Blockchain technology still has a first mover advantage to all types of organizations. It's also proving to be a powerhouse of innovation, with recent examples such as DeFi and more robust online identity management. Sure, there are many risks and challenges, but the evidence is growing that the opportunities are far too compelling to just stand on the sidelines. Organizations and leaders will need to decide sooner than later how they'll play in a world of blockchain and its related technologies. In this course, we've gone deeper into the details of blockchain technology and its emerging ecosystem. Blockchain begins to solve long-standing issues with trust, data integrity, and security. Fixing these issues alone could help to usher in the next phase of the internet. But hopefully this course makes it clear that blockchain has the potential to be so much more. We now know that blockchain technology can completely reinvent how we think about organizational processes and even the way organizations should be organized. The promise of a new internet ecosystem built on blockchain where all participants have a form of ownership is beginning to take shape. Known as Web3, it's an area to pay attention to and even get involved in. At this point, you may be convinced that there is a powerful future for blockchain and you want to be part of that future. Alternatively, you may have concluded it's too early or the technology is too speculative. You may even have decided that there's no future for this technology. If you've decided that blockchain is here to stay and its disruptive power is too great to ignore, then I have a few suggestions for your next steps. At a minimum, you should buy some cryptocurrency. The process of setting up an exchange account, transferring fiat currency, selecting and acquiring the crypto of your choice, and then managing it all in a wallet can be fun and informative. Remember, a good rule is only to spend as much as you don't mind losing. That is, unless you're a bold, risk-taking investor. Be informed and make the right choices for your circumstances. Check out my LinkedIn learning courses on cryptocurrency foundations and securing cryptocurrencies. You might also benefit from watching my introduction to non-fungible tokens, or NFTs. If a technical path is appealing, I recommend building your first Solidity-based smart contract on Ethereum. Refer to the Ethereum videos earlier on how to get started on that. If a business path is more up your alley, elevate this topic in your organization, or spin up an experiment with support from leadership. There's a healthy ecosystem of vendors, big and small, ready to help you. Finally, consider getting involved in a blockchain user group or organization. There are already many organizations beginning to service this area all over the world. Right now, there's ample opportunity for new voices and first movers. As the industry develops, we'll need a lot of new talent. Consider whether you want a career in this space. For the foreseeable future, jobs in blockchain technology will be plentiful and high-paying. Thank you for watching, and good luck.